For this sections, we're going to talk about linear approximations. We have seen that the curve lies very close to its tangent line. Now, it's really easy for us to evaluate the values and calculate the values of f of a, but the nearby points of f is really hard. Sometimes it's impossible to calculate. Therefore, we want to approximate by calculating the linear function whose graph is the tangent line of f. So that's why this sections we're going to introduce the linear approximation. So you can see that right here, the tangent line. This is the equation of a tangent line. So we're gonna try to approximate. Now, if let's say that point right there, if I try to zoom in, right, you see that the graph is gonna get closer and closer. The graph of the straight line, the linear equations, gets really close to the curve. So that's why we use the linear approximation for the curve. Okay, let's take a look at example 1. So for example 1, we want to find the linearization of the function right there. And then the point right here, a is 1. So what we're going to do is we're going to try to get the function, the linearization of the function. So first of all, I think I should rewrite because we're going to take the derivative. So let's just rewrite x plus 3 to the 1/2. I'm just going to do the derivative right now. So f prime is 1/2. X plus 3 to the negative 1/2. Let's rewrite. So what we have is 1 over 2 square root of x plus 3. So that's the derivative. Now let's plug in the point. So the point right here is 1. So f of 1 is going to be 1 plus 3, which is 2. Square root of 4 is 2. I'm going to try f prime of 1 as well because we need f of a and f prime of a. So f prime of a is going to be 1/2 square root of 1 plus 3, which is 1/4. Okay, now we're gonna write L of x. Okay, so by definition, L of x is, I'm just gonna rewrite the general form first. X minus a. Okay, so keep in mind a is 1 in this case. So what I have is f of 1 plus, what I have is f of 1 plus f prime of 1, x minus 1. So let's plug it in. We have 2 plus 1/4 x minus 1. If I simplify it, I ended up with, let's do the LCD. So 4 over 4. So if I simplify, I ended up with 7/4 plus x over 4. Because I distribute, you see right here, when you distribute, you have 1/4 here and then we subtract. So that's how I come up with 7 over 4. Okay, so you can see that the linear approximation that we have for square root of x plus 3 is 7/4 plus x over 4. Okay, so in particular, what do we have? We have square root of 3.98. So square root of 3.98. So that's 0.98 plus 3. Okay, so this is your x here. Okay, so what we have for square root of 3.98 is 7/4. I should put approximation. 7/4 plus 0.98 over 4. Okay, and then if you use the calculator, you should get 1.995. Okay, so for square root of 3.98. Now, they're also asking you for 4.05. Square root of 4.05, which is square root of 1.05 plus 3. Okay, so what do I have here? I have 7/4 plus 1.05 over 4. Okay, so what is the point for that one? If you use your calculator, you ended up with 2.0125. Okay. All right. So if you graph, you will see that the tangent line is going to be on top of the curve, so we overestimate. Now, even if you punch in your graphing, your calculator for square root of 3.98, you will see that the number is less than 1.995. So we overestimate here. But it's a very good estimation. Very good estimate. Now, let's take a look at differentials. So what is differential? So you see, we have we have y equals to f of x. Differential dx is the independent variable, and the dependent variable is the differential dy. Okay, so why do we use all of this? That's just because dy over dx is f prime of x. We have seen it before. We've seen this equation before. Okay, so we're going to use it to, once again, to approximate. Okay, now keep in mind that's the definition. So what we have for this example, we want to compare the values of delta y and dy. For A is from 2 to 2.05. Okay, so first of all, let's just evaluate f of 2. So f of 2, what I have is 2 cubed plus 2 squared minus 2 times 2 plus 1, which is 9. Okay, and f of 2.05, 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. This one's going to give me 9.717625. Okay, so for delta y, you just simply take f of 2.05, subtract f of 2. In this case, it's going to give me, so when I do the subtraction, I should get 0.717625. Okay, all right, so in general, what is dy? Dy is f prime of x dx. Don't forget I have dy over dx equals to f of f prime of x. So I just move the dx over, which is what? Let's do f prime. So f prime is 3x squared plus 2x minus 2 dx. Okay. All right. So what do we have? When x equals 2, dx is delta x, which is 0.05. I just take 2.05 minus 2 to get delta x. Okay. Now, let's solve for dy. So you see dy we have from the top is f prime of x times dx, right? So what I have for f prime is 2 squared plus 2 times 2 minus 2. And then I have 0.05. Okay. So I just want to make sure you are aware of it. So this part right here is f prime of 2. And this one right here is delta x. So if we use a calculator, we should end up with 0.7 for dy. For our final example, we're going to see the use of differentials in estimating the errors that occur because of approximate measurements. So you see right there we have a sphere with the radius is 21 centimeter with a possible error in measurement of at most 0.05. So we have the radius and we have the error. What is the maximum error in using these values of the radius to compute the volumes? Okay, so first of all, we need to know the relationship between the radius and the volumes. So let's say the radius is r, then the volumes. Hopefully you still remember the volumes of a sphere is 4/3 pi r cubed. Okay, so if the error in the measure values of r is denoted by dr. Okay, so this is the error. Then the error for v is going to be delta v. Error in volumes. So I need to find dv. So what is dv? Using approximation, I have dv equals to let's take the derivative. So it's gonna be 4 pi r squared dr. Okay, so in this case, you see that dr is 0.05 and r is 21. So I'm going to plug it in. dv is going to be 4 pi 21 squared multiplied by dr, which is 0.05. Okay, so if you calculate, you're going to end up with 277. Okay, so this is a large number, but this is the maximum error in calculated volumes. So this is I understand the number is still large, but a better picture of the error is given by the relative error. So you can compute that by the total volumes. That's something else.